thermal fluid sciences experts. This is ProReadyEngineer.
Hello, this is Bassam Abdelnabi from ProReadyEngineer. I'm excited to share a new video series featuring industry cases. If you like what you see, please consider liking and subscribing. Take care and talk to you soon.
You know, in the world of aerospace R&D, every single test, it's like a high-wire act. You're pushing the absolute boundaries of what's possible, and the line between a groundbreaking discovery and a catastrophic failure, well, that's measured in milliseconds. Today, we're going to break down the logic that keeps priceless hardware safe when theory meets fire.
All right, so here's how we're going to tackle this. First, we'll talk about the incredibly high stakes. Then, we'll get into the what-if problem that every single test team has to deal with. After that, we'll walk through the solution, look at the amazing results, and wrap it all up with the big takeaway. Let's get into it.
So let's really set the scene here. Why does this matter so much? Because in advanced combustion testing, the investment on the line for every single test run is just massive.
Yeah, and we're not just talking about the cost of a few parts. We're talking about entire seven-figure programs. All that time, all that money spent on design, analysis, and your best people. It's all riding on these physical tests going right.
And then you've got the hardware itself. Look, these are not off-the-shelf components. They're often one-of-a-kind, six-figure prototypes. They represent months, sometimes years of work. If you lose one of these, your whole schedule can get thrown completely out the window.
And here's the scary part. Disaster can strike way faster than any human can react. A sudden fuel spike, an acoustic overload, and boom. In the blink of an eye, you can go from a perfectly good test to molten metal and cracked components. And that unique prototype, it's gone.
Which really brings us to the big question for any engineering manager or CTO in this field. What is actually protecting your investment, second by second, when that flame is on? Because let's be honest, luck is not a strategy.
The real danger here, it's not any single part. It's the sheer complexity of the entire system. This is what we call the what-if problem, and frankly, it's a beast to manage.
Think about it. On any modern test rig, you have this whole web of interacting subsystems. You've got fuel valves, high-pressure VFD pumps, the ones that give you that super precise speed control, nitrogen purge systems, back pressure controls. They all have to work in perfect harmony. A failure in just one of them can cascade and pull the entire rig down with it.
And here is the absolute crux of the issue. The rig had individual controls. Sure, a valve can trip, a pump could have its own limits, but the core problem was that there was no single unified brain watching over everything. See, safety in these systems isn't just about how reliable one component is, it's about the coordination of how they all fail together. And this right here really shows the difference. On one side, you have the nightmare scenario. An uncontrolled shutdown is just chaos. Valves slam shut in the wrong order, creating pressure spikes that are just as bad, if not worse, than the initial problem. But the alternative? Control. A predefined, orderly sequence that brings the entire system to a safe state, every single time. So the big question is, how do you get from that chaos to that control? Well, you have to systematically untangle that complexity and turn it into clear, actionable logic. We broke it down into a simple two-stage approach. First, we had to define what safe actually means for every single component on that rig. And second, we defined the exact conditions, the triggers, that would set that safe sequence into motion. Stage 1 is all about meticulous, detailed planning. We went through every single control element and gave it a specific job in an emergency. So, for example, the main fuel valve, that has to close instantly to cut the energy source. But the fuel pump, you don't just kill it. You ramp it down smoothly to avoid a pressure surge. The nitrogen purge solenoid opens up, every single piece has its own specific job to do. Now, it's not just about what happens, it's about when it happens. The order of operations is absolutely everything. You have to isolate the fuel before you open that nitrogen purge. If you get that backwards, you could accidentally create an even more dangerous fuel-air mixture right inside your rig. It's that level of detail that separates success from disaster. Okay, on to stage 2. Once we knew what to do, we had to define exactly when to do it. So we identified these specific, measurable triggers, things like acoustic levels getting too high, a sudden spike in fuel pressure, a flame temperature overload, or even just the loss of a key control system. Any one of these events would instantly and reliably activate our safe shutdown sequence.
So what happened when we put this all in place? Well, the impact was huge, and honestly, it went way beyond just making things safer.
The single biggest result was this new level of operational confidence for the entire engineering team. They weren't just crossing their fingers and hoping for the best anymore. They knew a robust safety net was in place, ready to catch them.
And this created a fundamental shift in how they operated. Before, any unexpected event meant a catastrophic failure, destroyed hardware, and massive schedule delays. Afterwards, that exact same event became a controlled shutdown. It turned a disaster into a data point, something they could actually analyze to figure out what happened and then safely restart.
And the tangible impacts were just enormous. We protected those expensive assets, saving hundreds of thousands of dollars. Schedules became stable and predictable. And maybe the most important thing, discovery actually accelerated. The team felt confident enough to really push the envelope, to explore more aggressive test conditions, because they knew the system was protected by design.
So, when you boil it all down, what's the big takeaway here? It really comes down to a simple but really powerful philosophy.
The core lesson is this. In high-stakes testing, you simply cannot rely on luck. You have to rely on logic. A structured, well-defined protection strategy is the ultimate insurance policy for your hardware, for your schedule, and for your team's ability to innovate.
If this is a challenge that sounds familiar to you, I really encourage you to see the full technical breakdown. You can download the complete case study over at ProReadyEngineer.com. It's time to secure your next test campaign with logic, not with luck.